Today, I'm talk about how to convert quantum contextuality into quantum non-locality. And I will start by the obvious thing, defining what I mean by a Bell non-locality experiment. It's one in which we have two parties, Alice and Bob. Alice has at least two different measurement devices. Bob also has two measurement devices at least. They need somehow a composite physical system. They need space-like separation. They need the quantum system to be entangled. But it's important to notice that the measurements they are performing with these devices can be in principle destructive measurements. So there's no particular assumption about how the measurements are made. Why people is interested in Bell non-locality is because in quantum theory, you can define a set of models that can mimic local models that can mimic the predictions, and you notice that there are quantum predictions that cannot be mimicked by these models. So we have a set of local hidden variable models, which is the cyan one. Then we have the quantum set, and then we have the no signaling set. The first and the last are polytopes, while the quantum set is convex and it's in principle hard to characterize. Okay. In that context, a Bell inequality, a tight Bell inequality is exactly a condition that separates the set of local behaviors from the non-local behaviors. And we have also Bell inequalities that are not really tight in the sense the picture in the picture. Okay, then we have the Contextuality experiment in which we have a source and we have a first party which has several measurement devices as before, a second party that acts afterwards, time-like separated from the first one in general, who has also several devices. And here, composite systems are not needed. Space-like separation is not needed. Entanglement is not needed. But to claim non-classicality of the contextuality here, we need to assume that the measurements performed by these devices are sharp in the following sense. These measurements yield the same result when repeated and do not disturb compatible observables. And by compatible, I mean joint measurable observables, those that have a common refinement. Why measurements should be sharp? Because otherwise the assumption of outcome contextuality for contexts made of compatible observables is not justified appealing to classical physics. And there's a long list of papers containing arguments why so. But here we have basically the same geometry of behaviors. First, we have a set of non-contextual behaviors, which is a polytope. Then we have sometimes a quantum set, which goes beyond and is not a polytope. And both of them are inside a non-disturbing polytope. And again, here we can also define inequalities that we call non-contextuality inequalities. And we have tight non-contextuality inequalities, which are those exactly corresponding to the facets of the non-contextual polytope, and other inequalities that are not. But notice, and this is maybe an important point, that if and only if the measurements are sharp, then for any scenario, measurement scenario whose graph of compatibility is completely n-partite, and each part has at least two incompatible observables, which are exactly what we call typically a Bell scenario. And for instance, a square is an example of that. For these scenarios, the local set of behaviors is exactly equal to the non-contextual set of behaviors. The quantum Bell local set of behaviors is exactly equal to the quantum Cauchy-Specker contextual set of behaviors. And anything we call a tight Bell inequality is exactly a tight non-contextuality inequality. Why I mention this? Because there's this theorem by Vorobyev mentioned by Rui the first day, I think, that's saying that the only contextuality scenarios that admit contextual behaviors in the sense we are talking are those in which the graph of compatibility is non-chordal. That is, it contains induce at least a square, a pentagon, or an hexagon. Okay. Which implies the following. First of all, the simplest scenario in which contextuality with ideal or sharp measurements is possible is the one represented by a square, which is no equivalent of the closure or Simony-Holt Bell scenario. But we also know from Bell and Koch-Specker that in quantum theory, contextuality for ideal measurement can happen even with quantum systems of dimension 3. And the simplest scenario in which contextuality with ideal measurements on systems of dimension 3 is possible is precisely the one represented by the pentagon. These days, the Kliashko scenario. But why focusing on Koch-Specker contextuality rather than in Bell nonlocality? My personal answer to this is to understand why quantum theory. Because notice that quantum theory produces contextuality in absolutely all the scenarios allowed by Vorobyev's theorem. And notice that most of these scenarios are not Bell scenarios. So if we want to understand with principles single-celled quantum theory, or even if you want to understand Bell nonlocality, the safest way to proceed is understanding what shapes quantum contextuality in this sense. Good. But there are many reasons why people have not paid attention to Koch-Specker contextuality. Many people that love Bell nonlocality have never been interested in Koch-Specker contextuality. There are many reasons for that. They may argue that what we call sharp measurements are unphysical. By the way, this means that would mean that quantum theory is a theory about unphysical measurements, because quantum theory is essentially about these measurements. They may also argue that compatibility needed to define context for sequential measurements on a single system cannot be guaranteed in a sequential measurement experiment. Or simply they may argue that Koch-Specker contextuality for single systems can be classically simulated. How to attract Bell nonlocality fans, hardcore fans, ignoring Koch-Specker contextuality to the camp of Koch-Specker contextuality? Well, one possibility is by converting any example of Koch-Specker contextuality into an example of Bell nonlocality, an example which is somehow fundamentally connected with the original example. So here's a question. It's a technical question. Imagine I give you a set S of sharp measurements, which produce a violation Q of a non-contextuality inequality having bound K. Can two parties, each of them having this set of measurements, produce a violation Q, the same number as before, of a Bell inequality, which is formally identical to the previous non-contextuality inequality? In particular, it shares the same bound? Well, the answer is no. It sounds like impossible. Actually, the whole project, this whole result I'm about to present comes from a conversation we have during this year during the seminars. It's an old question, but Samson raises the kind of the question of how to produce, given an example of quantum contextuality, to produce a related example of Bell nonlocality. Here's the result I want to show today. Given any set of measurements that violates a non-contextuality inequality, this set can be enlarged by adding extra measurements produce a state-independent violation Q of a non-contextuality inequality with non-contextual bound K. And two parties, one of them having set, sorry, S, this is a mistake, having S union S prime, and the other having S union S prime, actually the transpose of that, can produce a violation Q of a Bell inequality which is formally identical to the previous non-contextuality inequality. Moreover, this, both the state-independent violation and the Bell violation disappear if we remove any element of the set. This is what links the Bell non-locality to the original state-dependent contextuality. And this is based on several methods. And there's first result that said basically that every quantum contextual behavior produced by a set of projectors, namely sharp measurements, violates all non-contextuality inequality of this particular form, in which we can link the bound to a graph, which is precisely the graph of orthogonality of the set of projectors. Okay. So the take-out message is that any example of quantum Cauchy-Specker contextuality you can imagine can always be converted into a violation of a non-contextuality inequality whose bound is the independence number of the graph of orthogonality of a set S of projectors. Okay. Then to define what I mean by a state-independent set. Okay. But basically it's a set of projectors that can produce, sorry, there's a mistake here, can produce contextual behaviors for any initial state. So you have this, you have the set of measurements, and no matter how you prepare the system, by measuring this particular set of observables, you can always detect, for any initial state, you can always violate a non-contextuality inequality. And some remarks is that principle, this state-independent set, contextuality set, might have projectors of rank 2, rank 3, but you can always recast, you can always convert any of this set into a set of projectors of rank 1. And then there's a result together with Matthias Kleiman and Constantino Budroni saying that a set of projectors, rank 1 projectors, is state-independent contextuality set if and only if, and there's here an addition, there's a set of non-negative numbers and a number y of these restrictions. So you have that. After many years, we have a kind of necessary and sufficient characterization of, given a set of projectors, decide whether or not they can produce state-independent contextuality. Okay. And in particular, we can take one of these 6 sets and produce a non-contextuality inequality of the form I presented at the beginning, in which we associate the bound of the inequality to the independence number of the graph of orthogonality of the projectors. Good. Some observations to compare this notion of state-independent contextuality set with previous, I mean, more well-known notions like the notion of Cauchy-Specker set of projectors. Remember that a Cauchy-Specker set or a Cauchy-Specker assignment, let's say, is an assignment of one satisfying that 2 orthogonal projectors cannot both have assigned 1, and that for every set of mutually orthogonal projectors summing the identity, at least one of them has to be the assigned 1. Okay. And a Cauchy-Specker set is one in which this assignment, a Cauchy-Specker assignment, is not possible. Here important things they got message is that, of course, all Coach-and-Specker sets are state-independent contextuality sets, but most state-independent contextuality sets are not Coach-and-Specker sets. Good. Then another important notion is the notion of criticality. This definition was introduced by Simba and Penrose. They said that a Coach-and-Specker set is critical if by removing any element of S, the resultant set is not a Coach-and-Specker set. For instance, the original Coach-and-Specker set is critical. However, as Otfried Kühne mentioned in his talk the first day, in the book of Asser Perez, and actually in the paper of Asser Perez in 1991, Asser says that some particular Coach-and-Specker set he's presenting is critical. Well, it was not. That's how we discovered the 18-vector Coach-and-Specker set. And following this definition, we would define a state-independent contextuality set as critical if by removing any element of this set, then the resultant set is not a state-independent contextuality set. Good. We also need a concept, many names in the literature, as becomes clear after Carl's talk. It basically is the building block, the basic building block of a Coach-and-Specker proof. It's a set of projectors with a particularity, which is assume non-contextual models and assign a particular assignment to one of the vectors. In any non-contextuality theory, there's another vector who has to have the opposite assignment, let's say. These sets are called differently in the literature, and names are true implies false sets, also definite predictions, 0-1 gadgets, or Hardy-like proofs. Okay. Probably even more names. Here you have an example of the first one with two representation, and you have here you can notice how these building blocks are the core of the original Coach-and-Specker proof. You have Simon Cochin here drawing one of these sets. And these sets are key for proving this result, which is the most technical part of the work, that actually is the key part, which is that any state-dependent contextuality set of projectors can always be extended to a critical state-independent set containing all projectors of the initials, and I insist, being critical. Then there's how to transform this SIG set into an example of Bell nonlocality. And here there are two ingredients. One is well-known since long ago, is the physical implementation. Here what we do is if the set of projectors is in a Hilbert space of dimension D, we prepare a maximally entangled state of two particles of dimension D. This idea was originally proposed by Alan Stairs in 1883 and simultaneously by Haywood and Redhead. Then Alice has S, meaning Alice can measure the elements of these sets of projectors, while Bob can measure the transposed projectors. Okay. This is very, this is the same Bob used many times before. And there's a second ingredient, which is a technical part, which is the proof that there is a Bell inequality, and you have it there, which is formally identical to the state-independent inequality that we had before. Formally means everything is all the terms, and in particular the bound is the same. Okay. To emphasize the difference between this second step and previous works, first of all, we should mention this, at least some of these previous works. As far as I know, the first one was the one by Alan Stairs, then Haywood and Redhead, and this creates at that time a long series of papers, about 10 papers. The one I most like is the Harvey Brown and George Spezlishny. Okay, then after After the GH set, there was also a rebirth of this thing, and there's a story of all versus nothing, and Bell inequality is inspired by Kochen-Specker proofs. Then there's a contribution by Arabin converting this into a game, which was named pseudo-telepathy by Brassard, and then incorporated in the vast field of non-local by many people, okay, including Samsung and Rias, as you can see. Let me emphasize what is the difference between the technical part of the second step and any of these previous attempts. This previous attempt, what they do, they convert some specific six sets, but they fail to provide a method to convert any six set, in particular duos type six sets. And converting to what? They can produce a game, but here we're talking about producing a Bell inequality and a Bell violation, and a violation of quantum violation of that Bell inequality. Actually, none of this work uses inequalities, no contextuality inequalities. Okay? And of course, then not preserve the gap between quantum and classical in the conversion. In addition, in the particular case of non-local games, most of them add extra constraints inspired by quantum theory, satisfied by quantum theory, but which are not satisfied by general non-contextual models. Good. So let me illustrate how the method works. Okay. Imagine you are given 5 projectors. Okay. These 5 projectors are, for instance, the ones used in the Kleashko experiment, and the Kleashko-Bell non-contextuality inequality can be written in this particular graphical form I mentioned at the beginning that you have here. If you prepare this particular state with this projector, you get a violation. Okay. We don't carry this particular violation. It's a state-dependent violation. Okay. So how the method transform this form of contextuality into a bipartite Bell inequality as follows. First of all, finds the minimal critical six set that contains the given projectors. And in this particular case, we can prove that this one, this is the minimal critical six set that contains the 5 original things. Can be proven. That's typically the hardest part. How can be proven in this particular case? Because the final set is the UO set, and we proved long ago that the UO set is the simplest in the meaning with the smallest number of projectors of rank 1 in any possible dimension. And recently, Sempeng Su and Matthias Kleiman have also proven that it also holds if you remove the assumption of rank 1 and you also allow rank 2 and rank 3. Then the next example is take the result of, with Matthias Kleiman and Costantino Budroni, identify the weights that provides the state-dependent violation, construct the corresponding graphical non-contextuality inequality, okay? And then you notice the following, that this inequality, okay, by the way, is you can also optimize to make the gap between non-contextual theories and quantum as maximum for this given six set. And in this particular case, after optimization, these are the weights, and this is the classical bound and the quantum value. And that's important. This is the quantum value for any initial state. Then you prepare 2 maximally entangled particles in dimension D, allow Alice to perform the first, what was the first measurement in the non-contextuality inequality, and Bob the second. Okay. Basically, the correlations between Alice and Bob then violate the Bell inequality, which has as local bound the bound of the original non-contextuality inequality, and as quantum value the original quantum value. So what are the virtues of the method? It works for any contextual correlations. It converts quantum violations of non-contextuality inequality that might only be testable in the lab, by performing sequential measurements on single system into Bell inequality that can be tested with local measurements on the spatially separated systems. Therefore, the so-called compatibility loophole, or also called compatibility sharpness loophole in contextuality experiment with sequential measurement, disappears in the Bell version. Okay, because in the Bell version, measurements do not need to be sharp. Okay? And also the compatibility is guaranteed mathematically by spatial separation. The quantum local gap of the Bell inequality, or the violation of the Bell inequality, is the same as the quantum non-contextual gap of the state-independent contextuality. And both are produced using the same measurements. Moreover, non-locality vanishes if you remove any element of the original set, the state-dependent set. Finally, this thing allows you to simultaneously test a state-independent contextuality inequality and a Bell inequality. Actually, you can even produce a test like this, in which just running the same experiment with two Bobs and two Alice, you are simultaneously violating first a non-contextuality inequality between Alice 1 and Alice 2, the same non-contextuality inequality between Bob 1 and Bob 2, a Bell non-locality which is formally identical to the two previous one between Alice 1 and Bob 1, and so on and so forth. Now Alice 2, Bob 2, Alice 2, Bob 1, Alice 2, and Bob 2. In all of them, the measurements performed by the parties are the same, the local and non-contextual bounds are the same, and the quantum values expected from the theory are the same. This is a very, very interesting experiment to make. And in particular, here there is no contextuality, non-locality trade-off as the one we found with Pavel Krusinski and Dagomir Kaslikovsky long ago, okay? Because here, the quantum violations of the Sikh inequality and the Bell inequality can be tested simultaneously in the experiments. Limitations of the method, except of the case in which the initial set is already a Sikh set, the non-local correlations resulting from the method do not have the same quantum local gap as the quantum non-contextual gap of the original dependent correlations. So references are these two. The first deals with the connections, the existing connections between non-locality and Cauchy-Specker contextuality. And the second introduces the method I try to describe in my time. Thank you for your attention.
Yes, my question is, you talk about measurements, but can't you simply talk about properties? Because your measurements are projective measurements, so they simply reveal which property the system had before it's measured, represented, and then the thing reduces to a discussion of projectors and non-commutation of projectors, tied in, I think, with some of Abramsky's ideas.
No, because if I talk about properties, these properties become explicitly non-local. They change because of the measurements, and explicitly contextual in the sense. That's why on purpose I just talk about outcomes of measurements. The moment I assume that these outcomes of measurements are revealing pre-existing properties, then the only way out would be to assume that these pre-existing properties change because actions made at a distance. And this is not necessary at all by the logic of the proofs. So no, despite the measurements are sharp, projective, despite that in any experiment, I'm just measuring compatible, commuting, sharp, projective measurements, I cannot say that of these measurements are revealing properties. If I understand properties as something pre-existent and permanent, I can't test that they are permanent, because whenever I repeat the measurements without making any incompatible measurement in between, I get the same outcome. In that sense, are persistent. but they cannot be pre-existent independent of the context, because this is precisely what the violation of both the Bell inequalities on one hand and the non-contextuality inequalities on the other hand are telling me.